final exam. Let's take a look at that quickly. Mute your microphone. All right, so let's take a look. We were looking at the calendar. Okay. Please, all right, so today is December 7th. We're doing our presentations today. And then on, we have finals during finals week. So let's take a look at that. PNW schedule. So that's going to be yeah. All right, sorry, yeah. I haven't shared the screen, so let me, sorry about that. All right, so as I was saying, I knew there was something wrong and I couldn't figure out what it was. All right, so as I was saying, you should be seeing my screen now. Today is December 7th. We finished all the topics. Today there's no lecture. And so we're only doing our presentations, and then we'll be done with that today. And then after that, all we have left is you should submit your Keras homework. So like I said, I'm going to leave it open until the last day, until let's say December 10th. And then the final exam will be, this class meets on Mondays at 2. Okay, so here we are, Monday at 2. So that means that your exam is Monday at 2:45. So your final exam will be Monday from 2:45 to 4:45. You can see that there. And so it'll be the December the 14th at 2:45. Okay? All right, so that's basically it from me as far as announcements. Now let's go ahead and get started with the presentation. So, we have plenty of time today to present, I would think. So, I think every group can take about 20 minutes. That would be a good enough amount of time. And we're gonna go in a first come, first serve. You'll present, and then don't forget to submit the materials. I've opened a Dropbox for that as well. So just submit the materials there. So given that we're going to do this on a first come, first serve, I need volunteers. So, who wants to go first?
We can. Joe and I can.
Okay.
I believe Joe's here.
Okay, great. So then group number 1. So usually I'll just take your names. And then after that, after that, you'll do your presentation and then questions. Okay?
Okay.
All right, so let's go ahead and get started then. Also, please, in the put your names on the chat on your login, just so that it's a little bit easier for me to see, to find your name. Okay.
Oh, sorry. What's that? In what sign in? Oh,
no, when you're logged in, right? When you're logged in, just you did, but I just.
Oh, I see. Oh, in Zoom. Okay, my bad.
Just saying in Zoom, if you can please put your names on there.
Could you enable screen sharing?
Oh, yeah.
Can you see my screen?
Yes.
Okay. So, yeah, more or less, this is our final project. Drew Johnson, partner was Joe Usbell. if he wants to start first, we can get going.
Sure. So the first part of the project is we went out and found a big data set. And I found it on Kaggle, and it was California collisions. So basically, the state of California put out a data set with like 1.8 million records in it of collisions that occurred in 2019 for some data mining. So it was originally an SQLite. I had to convert the SQLite into a CSV, and then I had to do some more data massaging to turn character data into numeric data, all with Python. After that, it dwindled down to about 1.4 million usable records, at least at what I can tell. Excuse me, when we ran the data set, we were only able to max out about at 520,000 records. And somewhere in that 1.4 million, there was, after 520, there was an error in 1 or 2 records, which we cannot find. So we just,
so it was an error not in memory, but you're just saying
in the data.
In the data itself. Okay.
Somewhere after all our data massaging, I missed a special character somewhere.
Okay.
Yeah, and it threw entire just errors for us.
Sorry, can you make your screen the other mode where it shows it a little bit bigger? Because I think you're showing now like the instructor version.
Oh, am I? Yeah, sure.
There's another there's another option where you. We were seeing the screen. It's just what I mean in the PowerPoint presentation you had.
Like, oh, did it? Yeah, where it had the next slide and everything.
Yeah, current slide and next slide. Just show the current slide. So
this one?
Yes.
Okay. Sorry. Yeah, I have 2 monitors and I couldn't tell which one was being shared.
Great. Thank you. Mm-hmm.
Okay. So yeah, we were able to run safely at 520,000 records. In the report, I guess I can include the Python scripts I used to massage and change the data as well. This is show you what I did, what Drew and I did on the big thing. It's probably more me having the bigger headache on it, but it's fine. And then yeah, we just ran it. That's some of the code snippet right there. What we did.
And then more of it. This was just literally just the, I guess, like meat of it, the actual stuff. So, or the actual algorithms and whatnot. And then, yeah.
So before you talk about the results, can you just talk about like the dimensions of X and Y? And then also I see you have a neural network architecture. Can you also talk about or I don't know if you were going to talk about those things, but before we get to the results, could you just talk about how many features, how many classes, those kinds of things? Okay,
so in this particular data set, we ended up with 29 different features. And then the samples was like 526,000 samples. So then I broke down all the labels, especially trying to classify on the accent if it was male or female. So there's 2 labels, 0, 1, or 0 for male and 2 for female, just trying to predict if things were accurately classified. So in our sample set, there was 2 labels, male, female, 29 features on top of that. And then the sample set was 526,000 samples. So then you can see our architecture, multi-layer. And we ran it like 3 or 4 different ways. Logistic regression, deep neural network, multi-layer, like 4 or 5 layers. Just a neural network with 2 layers. Then I ran another deep neural network, which is deep neural network 2, should be on there, which is I think 5 or 6 layers, just to see, just a comparison.
Sure. Why in the in your model I can see that the last activation is sigmoid. And you have 2 neurons on it. Did you try 2 neurons and softmax there?
Yeah, and just when we did the diagramming, and it just it just seemed to work better.
Okay.
When we were grabbing the metrics, because on some of them I tried softmax, and some of them I tried sigmoid at the end. I think the one with the, because like I said, I ran the DNA in twice, and I think one of them was sigmoid, and the last one I think it was softmax.
Yeah, what I do find interesting that the layer just before the last one, the one that has 16 neurons, that's a softmax instead of a ReLU there. What was your decision for doing that softmax instead of ReLU?
Just when we were doing the metrics to pull it up, it just seemed to basically graph better. It looked cleaner on the graph.
Okay.
Because I was running into jagged lines
Mm-hmm.
where it looked really choppy. You want that smooth ReLU curve, like the hockey stick curve.
Sure.
Some of it was like really jagged. It just didn't look clean. So then I switched to softmax. I got a cleaner curve on the ReLU.
Performance-wise, it was similar.
Yeah, I really couldn't tell the difference. I guess I should have put a timer to see which one would have been faster.
Mm-hmm.
But relatively, when I ran this on my computer, the whole process, taking everything through the script, took about 15,
You
20
guys gonna
minutes.
post this on GitHub?
Yes, we could.
I mean, it would be a good reference for yourselves. I think you have some interesting things in your architecture there. So you have a neural net, deep neural net, batch size. Okay. All right. The features. What was the makeup of the features? What were? Can you just give a few examples of what the features?
Sure. Like I said, so it was like 31. One of them was year of car, make of car, so like Fiat, Maserati, and then they classified it like sedan, two-door, if it was like a truck, a type of truck.
I have a question there. So if you're saying a car, right, and one of those features, Fiat, Maserati, you said, and another car, right? So you have, so what were the values there? Were they just numbers?
No, so I had to convert that. So it's actual names of the car and the make. So in my Python script, it ended up being 300 different types of cars.
Okay, so there's 300 types of cars in there, right? That's what you're telling me?
Correct, and I labeled them.
How did you solve this? Because this is actually a very important thing. So how did you address this feature?
So in my Python script, which I was going through, like, you probably think I'm crazy. I know there's an easier and probably better way to do it, but I just did a replace inside. I just did a string replace in. I didn't think there'd be that many types of cars. I did a string replace. So whenever I saw like Plymouth, replace it, let's say like 10. If I saw a Ferrari, replace it with the value of 5. So then it went from basically
You did
1
that
to
in Excel
300.
or something.
Excuse me?
Like in Excel, you're saying you did it manually.
I wish I could do it in Excel. I had to do it in Python. It was too big for Excel. But yes, it was a manual process.
There's a function labeler in Python that does that.
Oh, is there? Okay.
Yeah, there is one.
I'm a .NET programmer, and I knew how to do it in .NET, but I thought I'd try it in
But there is a function now. But so the conversion, the code, you can always find the function later. But the more important question that I can't let go is the following. So you had a feature type of car, and that feature had 100 words, you said, or something like that. And it ended up being that same feature type of car, but with 100 different numbers, one for each car type.
Correct.
Joe?
Yes, yeah, correct.
Okay, so, and that's it, right? You left the feature like that.
Yes.
Okay, so I can't not make the comment, and you wouldn't have known this because it's one of those things that, I don't get to cover, with all the topics in the class. But so when you have features like that, those are called categorical features, right?
Right.
So what I want to say, let's say you have from 0 to 100 cars, right? And Ferrari ended up being 100, but Lamborghini ended up being 1, right?
Yeah,
It's possible. And Fiat somewhere in there at 50, right? But see, there's a problem in that. The machine learning algorithm will immediately, because it creates an axis, on the vector space model, it's going to infer, okay, Lamborghini is a 1. So whatever this axis means, Lamborghini is not very much of it. Whereas Ferrari is 100, right, on the other range of the axis. So the machine learning algorithm will say, okay, whatever this axis is, Ferrari is a lot of it. And Fiat, which is 50, is somewhere in between. Do you see what I'm saying?
Yeah, I think it relates. So I had to, because this kept blowing up, and Google's a great thing,
But
and I had to do a convert to categorical. I think that's what fixed it.
But
what
you
you're
still
saying.
you still ended up with just the 30 initial features, right?
Right. Yeah. I'm not sure what categorical did behind the scenes,
The
but
problem is when you
Google
say
said-
categorical, where did you apply categorical? In the Python code, you mean?
yeah, in the Python.
But it didn't change the dimensionality of your
No.
X matrix, right?
No, it just
Okay, so
popped. An error popped up and said do two categorical.
that's what I'm saying. So let me do this. Can you guys stop sharing? We haven't a lot of time, so forgive me for interrupting you, but it's a very important topic, and I must address it. Okay, so let me share the whiteboard. Okay, so okay. Give me just a second. I had not, I didn't think I was going to do a writing, so I haven't set up my, my tablet. Just give me a second. So this is very important, a very important thing. All right, so all right, so what I understood from Joe's explanation, and sorry again for interrupting, is that you've got a matrix. You guys are seeing this now, right? Correct? You're seeing me writing on the whiteboard?
Correct.
Okay. And then you have 30. So this is your X matrix. One of your features, F whatever N, is type of car. Right? Fiat, Ferrari, whatever. But you converted that word into numbers. So we said Ferrari was 100. Oh, you don't have 1,000. 50, Fiat, Lamborghini somewhere in here. The problem is this vector in the vector space, Fn, will then get arranged like this. And it'll start thinking Ferrari goes here, Lamborghini goes here, Fiat goes here. Do you see that? And that's a problem because that's not true. There is no actual meaning or difference between, you know, in this axis, you randomly assign the numbers, right? So you could have just as easily have assigned Ferrari to here, Fiat to here, and Lamborghini somewhere in there and not there. Does this make sense, guys? By just the assignment of the numbers randomly. Do you guys see that? Guys?
Yeah.
Yes.
Right. So this, a lot of people, now it's not exactly wrong. Okay, it's not exactly wrong in the sense that, for instance, the machine learning algorithm might, because they all have the same pattern, at least the same number, it might figure out some pattern that works for it. Okay, so it's not necessarily that it's going to be, I mean, the machine learning algorithm at the end of the day might predict well. It might. However, because this is a class, I need to point out that this is not the right approach for this feature. Instead, what should be done is the following. And it's just because I've had a lot of encounters sometimes with, I get into really, really serious discussions about this, especially if there's statisticians in the room, not engineers. They have a tendency to be very picky about things like this. So I want to make the clarification that if you have this, let's say from 1 to 30, and this FN has, as you guys said, 100 groupings. Now, these are not the labels, grant you, they're just categorizations. You need to take this feature and blow it up. So what that means is you need to take the feature. Let's say that the data set is originally like this, 520, and it went to 30. But now that FN feature, if it has 100 values from 1 to 100, guess what? You have to create those features. So you would have, so let's say you had, from F1 to F30, and then now, let's say F7 was or let's call it F car, right? Car model. So that F car now needs to be blown up into FC1, FC2, FC 100. Do you see that, guys?
So like flattening the model almost, right? We'd have to blow it out.
You need to make it into a binary, basically. It needs to become a binary. Do you see that? Do you see what I'm saying?
I understand now. Okay, I wouldn't have thought of that.
Yeah, I mean, as I said, I've made this mistake a lot of times, believe me. And then I hear about it in presentations. Even if the model works, there's always the statistician in the room that is going to say, but that's not correct. And so I've learned those things over time, and just, this is the appropriate one. So I don't want to say it. And so basically now it becomes binary. So for instance, if this was 1, right, and then this is 1, so now this has a 1, and of course this feature goes away. Sometimes I leave it in there just to kind of see what's going on, but basically you're transforming that one into a spread. And so it's going to be a sparse, this one would be 1 here, and all the other ones are 0.
Zeros.
Do you see that, guys? And if it was Ferrari, remember this Ferrari, we said it was 100. So then Ferrari gets a 1, all the others get a 0. That's what you do with categorical features, because people will argue, but it's not true that Fiat is, so they're going to say, what is Fiat more of than Ferrari and Lamborghini? Cheaper, better? You know what I mean, guys?
Right, I see.
Guys?
Yeah, that makes sense.
Yes, no, yeah.
I'm not asking you to do this, of course. Like I said, I understand that sometimes the models work really well, but I'm just saying, from the point of view of this is how it should be handled when you have categorical features. So because remember, the feature that you have here in question is always, that's why this is the VSM, right? The vector space model. So the feature in question here always represents an axis, Rn, right, of an Rn space. And so whatever this axis is, it goes from an initial value to a max value. And what that represents is how much, where do you fall in that grouping? Ferrari, Italian cars, right? So I guess like, design and, luxury, things like that, right? Race cars. So, but this has a meaning. And so whenever you encounter features like that, you want to take this approach. Make it binary. So this would be one hot encoding in a way. So, you know, you guys have taken 530, so you remember one hot encoding, right?
Yeah.
So it's exactly almost like one hot encoding. For those of you that haven't, you know, that's something we cover in 530. One hot encoding takes one column. So that applies not just to labels, but the features in particular, because you don't want the categorical element in there. So are there any questions about what I just said? And like I said, I'm sorry to interrupt, but you just brought up such an important thing. You know, it made a lot of sense to do it here. Any questions, guys? For the rest of the class, did you guys understand?
Yeah.
Yeah.
Okay, excellent. Thank you, guys. Okay, great. So sorry, guys.
No, that was helpful. I kind of.
Continue. Yeah, great, great. Continue.
Let's see if I can figure. There we go. We're back to the screen. Okay, and then. Joe, did you want to talk about the results?
Yeah, so these are our results. You can just sort of see. So you know, it's based on we did a train split, and then you know did the randomization on grabbing the records. So the accuracy, you can see some of the metrics aren't that great. You know, closer to 1 the better. So I guess to say the data set isn't that great, or our architecture isn't that great.
So in this model, what's the best? What's the best model in your conclusion?
The deep neural network looks to be the best.
ENN2, okay. F measure of 0.68 with all the data.
Right. Yeah, it's right.
And then yeah, these are just the kind of the graphs that popped out at the end.
Okay, laws. Yep, that makes sense. Did you guys use the Scholar GPU boxes?
Actually, we ended up not. We were able to kind of run it via our computers.
So it was enough in your
Yeah, we had enough. Yeah. And then okay, so images.
Oh, sorry.
Go
Did
for
you
it.
run this on Windows or Linux?
Windows.
Windows, yeah, okay, great. So everything with, I know Joe was using Windows before, so everything with Windows is working well now.
Yeah, I even kind of switched to Windows. It's kind of easier for me.
Are you using the Anaconda environment?
Yeah.
Okay, got it.
Yeah. So okay, and then yeah, for our images, we got like 100 images of just literally 80 by 60 pixel pictures of clothing, and so we split it up into 4 different categories. We had 25 shirts, 25 shorts, 25 shoes, and then there's the final one was just 25 other, which just more or less consisted of all backpacks or hats. It's just a sort of an easy data set to find, and I was kind of, you know, would be interesting to see. We ended up using just CNN for it. Here's, you know, the top right is splitting up the data into the different categories, and then bottom left is just the architecture. Basically.
How did you read the data? How did you read the data there?
So I just had literally, so I went through the entire directory. I named all like the, you know, shirt 1 through 25, short 1 through 25, and then just kind of went through that directory, opened it, put it all into an array, and was able to do that.
And you didn't flatten the images, right? Because I can see you have 80 by 60 by 3. So you just loaded everything basically as a tensor into the CNN.
Yeah, and it ran out well. I tried running it. I did try it on bigger images, and I immediately ran out of memory on.
Yeah, that'll.
Oh.
Okay.
I that's kind of why we ended up sticking with this one. It was small enough to end up actually being able to run.
Getting in there, okay.
Yeah. The thing with this one, it did pretty poorly. I ran about 1,000 epics of it. It only did 25%. I have a feeling that if we were to have been able to get more or use more data, it would have it could have worked better.
Yeah, deep neural networks need a lot of data, right?
Yes. Yeah, and so the problem I wanted to do more. The problem I was running into was there were random images within the data set that were different than the others, and I have no idea why they weren't like it was still 80 by 60, but there's something in it that just was completely different, and I couldn't figure out what the difference was. I was looking, I just could not figure out.
Were they images with like other things around them?
No, I don't think so,
Do
but
you have
I
an
could.
example of the images?
Honestly, not on this computer.
Oh, okay.
But yeah, it was literally just a close-up picture of a shirt with sometimes there's a person in them, and but it was just I inspected it, I looked, I could not figure out what was different about them. And then out of the 100 that we ended up choosing, 2 of them were broken and the other 98 were fine.
Did you
And
do
they
a distribution matrix just to see if it did well in at least one of the categories?
I did, but I forgot to get a screenshot of that. It did pretty poorly in all of them.
Okay.
Yeah. I like you said, I think just getting more data would have been the way to
I'm
increase
trying
it.
to think with the CNN. Can you bring up the CNN architecture? Let me just take a quick look.
Yeah, it might have been. Yeah, I probably could have changed it a little bit better to do it a little bit differently. It was just I kept running into a weird error, and
You have about 3 convolutions
mhm.
and 2 fully connected layers.
Yeah, and honestly, once I kind of got it to run super late, last night. So honestly,
Look, there's something that I just noticed in your CNN. So CNNs, I'm not saying that this is going to necessarily give you better results, but there's something that you probably want to address. You want them to be like a funnel. So they start big and get smaller over time. And yours seems to be, what are the dimensions of yours?
Oh yeah, they're quite big. And
Let me just think about this before I, I'm going to check my own book here just before I say something wrong. But I'm going to look at I have an architecture in there. Now I don't know what like I said, a lot of this is very experimental sometimes. So usually, now the filters is okay. You can have more filters, but well, you have the max pooling actually. So no, it's okay. It's okay like that. So you can have more filters after. That's fine. It's in the convolution where it should be, and you did max pool it, right? Okay, no, so it's fine. It's
okay.
fine. I take that back.
Yeah, I didn't, like I said, I didn't experiment too much with it, which I could have, but I was running. It took me forever to figure out that it was just those 2 images that was running it. And so once I kind of got it running, I was.
So I'm just saying for the rest of the class, where he's got 16 and 32 and 64. Usually in a neural net this increases, but in a CNN actually standard practice is you can increase the number of filters, but then you have the max pooling that cuts it short. So like I said, if these guys have taken 530, if you take 530 later, you'll understand a little bit more. Yeah, unfortunately, I don't see anything right now, guys.
Yeah, I think a lot of it was just a small data set because there's 25 images.
What I would have suggested is instead of 4 classes, just have 2 and start there.
Yeah, I kind of thought of that as well after, but I was just I was kind of curious to see what would happen with it being all that that data.
Yeah. Okay. All right. Well, yeah, great.
So, and then
you have results or anything else?
just that was about it. I just had that little, just that printed out a little bit. It did pretty poorly on kind of across the board. Just
Okay,
I
that's
think
fine.
lack of
That's
data.
fine. You did a great job. That's how machine learning is. All right. So I don't have any more questions. You've addressed everything. So for the rest of the class, you've seen what the kinds of questions I asked of them. So if you just already answer those questions, I may in the end have no questions. Okay, but these are the things that we all need to understand. All right, so great job. So now I'll open it to the class. Do you guys have any questions for them? Any questions for Drew and Joe? No? All right, great job, guys. So applauding here. So excellent. Thank you.
Thank you.
All right, who would like to go next?
My group can go next. Me and Neil.
Okay, Neil, Buzz, and
Hello.
and Josh. Okay.
Am I free to share my screen?
Yeah, please, you can begin.
Okay, so this is our final project by Josh and me. I actually started off with the results and then went into the, give me 1 second, and then went into the code. What I did is I grabbed a large data set of pictures. So this was cats versus dogs. And I ran 6 convolutions in order to see how the accuracy and the performance was. So as you can see, it starts off the percentage really low and then it increases up. And then this is kind of a graph how the machine learning worked. So as you can see, there's some pictures with cats, some pictures with dogs. It got about an 80% accuracy towards the end of it. So which is why, like, for example, the bottom left picture, obviously that's a dog, but it thought it was a cat. So it takes certain things and it'll sometimes make a mistake, but 80% accuracy was pretty good. That's about as high as I could get it up to though.
Really
And
good,
then
actually.
and then I tried it again with 10 convolutions, and it didn't perform as well. I'm pretty sure it's because my computer couldn't handle it. But
You didn't use the GPU boxes?
so going into this, I have a really good GPU. I have a
Oh.
2070 Super, and then last minute I had to leave my house for a while, so I wasn't able to run it on my actual desktop, so I had to run it off my laptop.
Okay.
And it was just a hassle trying to get everything reconnected and configured, so I just ended up using my laptop.
Okay.
So yeah, I apologize for that. It was a last minute thing. And then I ran it again. This was over 10 epochs, by the way. And for the red graph, it kind of messed up because I reran the 6 convolutions, but I ran it at 2, 4, 6, 8, and 10 convolutions, and I'm pretty sure at 8 convolutions is when it started to like die out. And at the 2 and 4, it just didn't perform as well as I would have hoped it to be. And then at the end, I had it write to a CSV file. So you would have your picture ID. So it was whatever the ID of that picture was. And then the label would be the percentage that it would think it was a dog. So how dog-like the picture was. So for example, for ID1, it was about 60% confident that this picture was a dog. And it went through that entire data set doing that.
How did you do this?
I used it was some function I used in the
From the convolution model?
yeah, it was some function I used from the convolution model that was able to write it. Sorry, I'm looking through my code right now and I'm trying to figure out where I wrote it. Yeah, I just
model predict there.
yeah. So it Yeah, it was model.predict is how it wrote it, and it formatted it in that way.
So can you talk a little bit about the data set, the X and the Y features, labels, just like
Yeah, so I mean, there was only two features. It was whether it was a dog or a cat.
labels.
Oh, labels. Yeah,
Any
so
features?
yeah, I'm not too sure about the feature part.
Okay. It's the size of the images, right?
Yeah. Oh, yeah. So at the beginning, I just changed the image to be 50 by 50, so all the images were consistent.
Okay, so it's 50 by 50 by 1 because it's black and white.
Correct. Yes. So yeah, and then this is a little bit of my code. I apologize for the blurriness, but yeah. So as you can see, I have image size, which is declared as 50, and then I have a learning rate of 1e-3, which is a little bit slower, but it was able to work for my laptop, which was nice. And then I had made the model name, and then this one I used 8, but you can change that 8 for 6 or 2, which is what the model was named. And then this is my convolution network. So as you can see, I have each pairing. So there's the 32, and then there's the 64. Each would be like 2. So in total in this one I had 4. And then there was I believe 1 layer. And then it would just write a regression. Yeah, and that's pretty much the bulk of my code from my part. Oh yeah, and at the top you can see the image size, so it would be 50 by 50, and then the 1 for the input data part.
Okay.
And this is Josh's part.
Yeah, so I thought we were doing the whole pipeline, so I ran it through Weka, SKLearn, and Keras. But I'll explain my data. So I got a file that has different ransomware attacks on it. It was just under 3 mil.
3 million?
Yeah.
Oh yeah, I forgot to ask Neil. I'm sorry. How many samples did you use, Neil?
I believe it was 100,000.
100,000. Okay.
Yeah.
And was it a balanced data set? What that means is that you would have, half roughly of cats, half roughly of dogs.
I believe for the training data set, it wasn't balanced, but for the test data set, it was.
When you say it wasn't balanced, what do you mean by that?
I mean, it was just a random arbitrary number of dogs and cats. It wasn't like 50-50.
Right, but even if you had like 30-70, it's roughly balanced. What's highly imbalanced is like 5 to 95.
Oh yeah, then in that case, yeah, it was balanced. Sorry.
All right, great. Yeah, sorry, Josh. Continue, please.
Yeah, so my data set was just under 3 mil instances. The label, so these are all the different features of the data set. So we have the year that the attack was discovered, the day, the length, the weight, the count, the loop, neighbors, income. And then the label itself is just the different types of attacks. If you can go to the next slide. So yeah, sorry for the blurriness. But this one, you can see the different labels here. You can see how many was in each one, and you can also see the number, the numeric value was translated to. And this goes across all 3 of the
So you're
different types
saying
that I did.
how many attacks are we talking about here?
29 total.
20. That's a lot of classes for a classification problem.
Yes, and I would talk about the different. I ran into a lot of problems later.
Okay. Now what I can say is I see. You could group what I've done with this sometimes is I group them. I group them into type of ransomware as opposed to individual ransomwares.
Yeah, that might have been and as I will explain later, I honestly did run into a lot of different issues. So that might have been like the better, idea
Yeah,
for me
it's
to
a lot
do.
of labels for okay, go ahead.
Yeah, next slide. I'm just gonna go through Weka first. I only ran it with one type inside Weka, which was naiveBayes. This is just a summary from Weka. You can see it did about like 30% correct. This is actually the lowest that I got, surprisingly. Next. This is just the accuracy by classes. You can go to the next.
Okay, hold on. You
Oh,
go
go
back.
back.
Go back to all right, yeah, so they're pretty low. F measures there, are except for one, 0.40, no. Did I thought I saw something. Okay. Oh, yeah.
The white is the largest data set, so it makes sense for it to have the best like F measure.
The white is the class, the ransomware that has the most samples, you mean?
Yeah, so if you go back 2 slides, I believe, Neil.
One of the go ahead. Oh.
Yeah, you can tell the
Oh yeah.
Account.
So yeah, I mean, it's never gonna find those like Montreal APT, Comrade, Sam. I mean, there's like one sample.
Yeah.
So there, definitely you need to group those. So I would expect those top ones, there's more samples there, and the bottom one, yeah, that dominates completely.
Yeah.
3 million.
Go to the next, go 3 over, I believe. Yeah, so this is the confusion matrix that came up. You know, if you want to look at this, but we can go to the next slide. This is, I did a feature ranking. Surprisingly enough, I thought the highest feature ranking would be income, so how much money each ransomware took, but it was actually year, so I guess it based off like which year, you know, each one was more popular. So that was an interesting find to me. Next. So this is with the SKLearn. I ran it in 4 different algorithms in SKLearn. As you can see, like all across the board, surprisingly, it did much better.
I think it's very, very strange that.
Yeah, I did as well.
That F measure will be 0.98. I would understand accuracy. Accuracy is misleading sometimes, but F measure, precision and recall, above 90 with that data set, there's gotta be something wrong. It can't be.
Yeah, and this was something I was, I've been working on this all the way up till today. So by the time I submit the final findings, my stuff will look a little different because
because Weka and they're not gonna be inconsistent. So these should have been a lot lower. So we'd have to look at your code. I mean, there's some error. Are you sure you're loading like this data set and not some other data set?
Yeah, no, I loaded this data set. I set the right labels. I set the right, for X and Y's.
You should do it in your data. First of all, get rid of those 29 classes and just group everything really into, I don't know, because you have a highly imbalanced data. You have a data set of only ransomware, correct?
Correct.
It's not like you have ransomware and non-ransomware. So it's only ransomware.
Correct.
Yeah. And one of them is 3 million.
Correct.
And then the others don't even make up, I think, like 30,000 from what I saw. So you have a 30,000 to 3 million. That's a highly imbalanced data set. You see what I'm saying?
Yeah, no, I understand.
And so if anything, it would just be that 3 million one versus the rest, if at all. But it, I'm not saying you have to change it. I mean, I honestly like data sets that are difficult like this because, we can think about things, but that would be my recommendation. Just go back to that where you showed the data samples total.
Yeah, I believe it was the first. Oh,
right. So if you look at that first one is 2,875,284 white, right?
Yeah.
And so and you said there's like 3 million samples. So the rest is at most 40,000. And so it really should just be those 2 classes if there's any logic in separating them out. I don't know what the difference is between the other one. All of the other ones say Montreal almost, right? So.
Yeah, no, that makes sense. I pulled this data set. I'm sorry, I need to remember the name of the website. It was from the UCI machine learning repository. So yeah, I mean, that would make more sense. Like I said, I do plan on working
Yeah.
on this some more. So in my next submission, I can actually do the comparison of the two, just because it is weighted. So like,
Yeah, this is a
Heavy.
highly imbalanced. I mean, this is a
Yeah.
complicated data set. I grant you that.
you can go, what was it like? Yeah. So this is SKLearn. Like I said, I was having tons of problems in this. Um, and I just did the neural network and I did a logistic regression one. As you can see with the logistic regression, and like I said, I was working on this up until today. So like I was only testing with one epic. So this is only one epic's worth of like rounds, but you can see just from the logistic regression, it looks way better than the SKLearn with the F score. One score, and for some reason my neural network didn't populate, so it's something I'm still working on, like I said.
Mhm.
So those are just things that I'm still currently working on.
Okay.
I believe that is it. I did not add any of my code to the slides. If you like, I can show my code.
Well, it's useful to see in particular the Keras neural network, right? That that's what you guys are playing with. So.
So yeah, if you like, I can share my screen.
No,
I
if
can
you don't
show
have
that.
it, you don't have it, so it's fine.
Well, I have it on me. I just didn't add it to the slide.
Yeah. Like I said, what I find is very strange, the results, an F1 score of 76 on that data set. So what
Would you
I
like
would
me to share?
recommend is double check, that's what what I'm going to say, double check.
So would you? I mean, so are we done, or do you not want to look at my?
No, you can show it. You can show your
Okay.
Do you want me to stop screen sharing?
Yeah.
Okay.
How does that look? Does that need to be in size increased?
That's fine.
Okay. Um, Again, I was doing a lot of testing, so
Where did you load the data? Did you slice the data correctly?
this is where I load my data from. I was doing the XOR over here. This is just testing. I was doing the XOR here, and I did a 70-30 split for testing.
Mhm. Okay. Yeah, but your real labels, right? Those are the ones that from new file
Wait, I'm sorry. What do you mean by
index.
real labels?
Sorry? Because when you have that Y over there, that, what you just enabled, that creates XOR labels to your data set randomly, right? But you want to use the labels in your original Y, right? So you need to comment out that those two
I'm
Y.
sorry, my connection. I have bad connection, and the last couple of things you said dropped out.
Well, I'm just saying the XOR that you enabled, I'm not getting why you enabled that. That should.
I was just showing that's what I was doing initially. I had it commented out because it wasn't
Yes.
working.
Right, but it won't, right? Because
Yeah.
the labels have to come from your data, new file too. I assume that's your ransomware data, correct?
Correct.
And so you have 3 million samples there, and from 0 to 8, that's the features, and then the 8th column, that's your labels,
Correct.
your 29 labels or whatever it is, right?
Yeah. Yeah.
Okay, that's what needs to be running, not, yeah, okay. All right, do you have anything else to say?
No, that was about it. This is just the rest of the code that I was working with. I had to make sure I was doing categorical, instead of the binary. But yeah, that's about it for me.
Okay, any questions, guys, from this group? No? All right. All right, and who would like to go next? Thanks, guys. Great job.
Thank you.
Thank you.
All right, who would like to go next? Mitch? There's a problem with your audio there, I think.
Yeah, can you hear me?
Can you speak up a little louder? We can't hear you very.
Can you hear me?
Yes, better now.
Let's see.
Was the one talking before? I just want to make sure my audio is good then.
Oh, you have like a loud buzzing. Marianne, you ready to share the screen?
Are you having trouble? Would you like another? Oh,
Yeah, I think we're good right now. Marianne, is your mic working?
Yeah.
No, there's like a loud humming. I'll just talk. Just
well, there's a buzzing coming.
yeah. We could have another group go while we try to
Okay,
figure
all right.
out
You guys want to
technical
figure out your
difficulties. Yeah.
Yeah, that's fine. Kyle, are you guys ready to go?
Yeah, I can go. I work alone.
All right, guys, please go. All right, so Kyle, who else is in your group, Kyle?
I worked alone.
Oh, you. All right. Well, you have the floor, sir.
Am I screen sharing the right screen?
Yeah, we're seeing the presenter. Just I guess start the slideshow.
Give me 1 sec. How about now?
Great.
Okay. So I'm Kyle. So my big data set was this SUSY data set from UCI. It had 5 million samples and 18 features, which are listed here. I'm not really familiar with the actual features themselves. Those are just what was given.
It's something to do with physics, right?
Yeah, so the abstract is that this was a classification problem to distinguish between a signal process which produces supersymmetric particles and a background process which does not. So something related to signal processing.
So there's 2 classes, 18 features.
Yeah.
And 5 million samples. That's a really big data set.
Yeah, so the first thing I did was make it smaller just for testing purposes. I did my everything in GPU Scholar. So the 5 million did load up until like yesterday night and this morning where I was having issues with it, but I can describe that later. So this was just a Python script I wrote to shrink the file down so it'd be easier to test and mess with. You can see I cut it down from 2.4 gigs to 48 megabytes, which was really nice because it ran really fast.
Good. Excellent.
So because I was having issues running it in GPU Scholar, I did all of my like results for both the small subset test and the big one when I could. So there will be like duplicate screenshots for this part. This was just me plotting the data. This was using the truncated SVD thing we did in class last week.
Right. Okay, excellent. Interesting.
This is what they looked like without that. So this is just the normal scatter plots. So here is the SKLearn metrics for this smaller results, or the smaller file. Both the files were pretty similar. The bigger one, I think, did perform better, but I don't have those on hand because Scholar keeps killing my program, and it only started doing that a day ago, so that was really unfortunate. So I do have to finish this part whenever it'll let me actually run it. I've been doing most of it later at night, and I've had no issues until yesterday. So this was my Keras and the results I got for both. I'm still not super familiar with making the input layers and such, so I was just kind of like trying whatever I could think of to get it to work. And then I was just going with whatever gave me the best results. So having more data did give me slightly better accuracy.
So these are different architectures, right? That's what you're,
Yeah,
the first one is like logistic regression. The second one is a deep neural net of 2 layers, and the next one is 3 layers.
yeah.
Okay. Good.
So these were the graphs. This one is for the smaller data set. They're pretty smooth, except for the deeper neural network that I did is a little bumpy for this small data set. But in the bigger one, everything is a lot smoother.
This is for the 5 million.
Yeah, this is for the 5 million.
So Scholar ran Keras with 5 million.
Yes.
Okay. What's the, let's see, so your accuracy, 70, 80, 80.
Yeah, it's right around 80, yeah.
Did you do the other metrics like F1 measure?
I didn't print them out in here. I have them running for the epics, but I didn't grab them for this. I didn't have
Did you
time.
look at them at least?
Just glanced at it. Nothing that I remember.
You don't
was
remember
super...
if they were good or bad?
They weren't terrible. That's all I can say, because like it didn't cause alarm. So
Well,
I
you
don't
only
remember
have a
exactly.
class problem, right?
Yeah.
Okay. Did you do a confusion matrix by any chance?
I don't think so. No.
It's always good to take a look at, so this looks promising and it makes me think that it did well, but just, you know, corroborate with a confusion matrix F1 measure, just, you know.
Or well, I have a small confusion matrix from Weka because I ran the smaller file on that. So
On
I
the
can show you that
smaller one?
later.
Did, when
Yeah.
you selected that 100,000 from the smaller one, did you select those values randomly?
I don't think so. No, I should have, but
Like the top 100 maybe?
yeah, it was just the top 100.
So for your experiment to be a little bit better with,
It would
with
have to
the
be
whole-
random.
Yeah, because
Yeah.
it would just give it a little bit more, statistically 100,000 out of 5 million, if you
It's
pick
not-
them randomly, would possibly be correct. You know what I mean?
Yeah, but
So
not when they're just in a line.
if you just take them from the top, it's not as great as if you had done it randomly, is what I'm saying.
Yeah, it was more just for me to get it going, and then I was gonna maybe do that if I had time.
You've done a great job. I'm just saying that would make it, you know, it's like
Yeah.
in a factory, right? If you have a whole bunch of radios and you're checking them, you don't just check one batch because maybe that was just a batch of the employee that's really good, you know? So,
Yeah, you take a couple from all the batches.
yeah, you do it randomly and then that gives you a lot of confidence and you don't have to check all of them. So it's the same here is all I'm saying.
Yeah, I just didn't have time after
Sure.
I started not running my program. Okay, so these were the Weka results. I just did 4 different classifiers. They're
The
similar
small, the
to.
small, right?
Yeah, this was the small.
F measure 70s, 70. Naive. Which one? Okay, what are naiveBayes, decision trees, KNN, logistic regression, 70s. Okay.
Yeah.
2 classes, right? 2 classes.
Yeah, 2 classes.
Got it.
You can see the matrix at the bottom for each one.
Yeah, I see that. Great.
Okay. Obviously, I couldn't run the bigger one in Weka because it's huge, and even that one was giving me issues sometimes. And then this is feature ranking for the smaller set. I wasn't sure how to do feature ranking on the bigger one, so.
Right, we'd have to implement the algorithm like, you know, information game or chi-square, but we didn't cover that in this class.
Yeah. Okay, so for my raw data, I grabbed 31 images.
I'm sorry, we saw the, can you go back to the Keras part of the big data, just really quickly?
This part?
Yeah, this part, right? So which one of these did better? That was my last question.
The bottom one, so the deeper
So
neural
the
network.
deeper neural network did better.
Yeah. So this is just, they're exactly the same 1-to-1. So like they're in order, both of these.
So the last one did the best.
Yeah, which would be this big one.
The deeper. Okay, got it. That's all I wanted to know. All right, great job.
Okay. So for my raw data one, 31 images of birds. I just found these on Google. 9 were blue jay, 8 were cardinal, and 14 were robin. I used the code that you gave us to make them into 120 by 80. And this is what they look like when you shrink them. You can see they're slightly distorted, and they're also labeled here as well.
So this is gonna do well by the color, I would think.
Yeah, well, kinda. I don't have that many samples, and I think that's what hurt me, but you'll see. So I was having issues passing the tensor to the neural networks because I have a similar makeup I'll show you in the next slide. So I reshaped it to a 2D array. I think this works. Like it runs and stuff, but I'm not sure how, like, if this is a good practice or not. I'll show you more. This was just me plotting them again with the SVD and then the normals on the right. This was the SKLearn results. It does not do well, except for logistic regression does well. I'm not really sure why, because I think I implement it with Keras and it doesn't do well at all. It does the best out of all my Keras models, but nowhere close to 78. So here's my accuracies. It's a similar models to my last one. They're just slightly different. I was just trying basically anything I could think of.
So so you only have two. Okay, so you only have 2 neurons though in that deep neural net. The last one, you see 2, 2, 1.
Yeah.
Shouldn't you have more? I mean, you
I've
have.
tried.
You start with images that are 80 by 100. So they should be shrinking, funneling, but think about it, from 80 by 100, you don't want to just jump to 2 neurons.
Yeah, I tried with bigger numbers and everything. Like, I might just be an error I was having, but I
think your problem was in that initial input shape that you were talking about. Here it would have been, let's say that deep neural net, right? So your images were 30 images by 80 by 100 or so by 3, right?
Yeah, 8123.
Yeah, so then here in the first layer, I would have done, first of all, you have to flatten them because you're not using a CNN. So you would flatten them and then...
Well, do I have to flatten them if I reshape them?
Yeah, you have to reshape them to a flat line, yes. A one single vector because you're feeding a vector. See, you're not doing what they did with the CNN. You know what I mean?
Yeah.
Which is, like I said, it's a topic in 530, so you're not really expected to know that. So really, maybe taking 80 by 100 and flattening it, but then these layers should be a lot bigger than just 2, 2, and 1.
Yeah, I was just trying anything. But
all right. So what I would recommend if you want to try it is flatten that vector, right? The initial input, to reshape it from 80 to 80 to 3, right? Into one single vector. And then here, these layers, instead 2, 2, 2, and 1, you probably want to have like...
I tried bigger numbers.
Go ahead, sorry?
I tried like in the thousands and they didn't do anything different. So I think there might be some other issue I had.
Yeah, there's probably in the input, then that's where I would think is the problem.
Yeah. Because no matter what I was doing, I was getting exactly 22.
Yeah, just straighten it. That would be the recommended practice.
Okay.
I would say.
So these are the graphs.
So the value was what? 20 accuracy?
Oh yeah. 44 was the best for just the logistic regression.
Okay. Got it.
So that's the first one on the left. I'm thinking there's just something wrong with my deep neural network because I don't think it's supposed to be straight lines.
I think it's the input that's the problem.
Yeah. Which I'm not really sure why the rest would work and that one wouldn't, but I didn't have a ton of time to test everything. So. And then I did Weka as well for this one. The results are pretty much similar, except for J48 did pretty well. The confusion matrix are there. I cut this one off, I think, a little bit on accident, but. And then the feature ranking is here. then basically my big data was good until it stopped running. So I kind of got cut short on some of the things like the SKLearn part. It does work. I just didn't get screenshots of it because I ran it a while ago. I would have liked to find more bird images given more time because I don't think I had enough to make it work well.
I think, I agree with that, but also the input is very important. There's something there. Normalize the data also, you know, those.
Yeah, I normalized it, but I don't know if I did it
Take
correctly.
a look at the code. I do have some code for loading images and straightening them, actually. If you stop sharing, I can, well, finish your presentation.
Well, this is pretty much it. I just need to spend more time learning about the models because I'm not
So
super familiar with them.
let me point you to something, okay?
Yeah, I'll stop sharing.
And this is something that, as I said, it's something we cover in 5:30. So are you guys seeing my screen now?
Not yet.
Not yet, okay. All right, so if we go to, so you should be seeing my screen now.
Yeah, we do.
And if you go to, I think it's in here, RGB. Do you see RGB?
Yep.
Okay, so in RGB, I have an example here. These are images, right, that I have. And then here I have the code. And if you take a look at, well, the whole of it, really, don't worry that this is in TensorFlow 1. You know, this will work in any Python. But you can see this loads the images, and then it's going to show you little tricks on how to resize things. But basically, it flattens them so that then you can have a neural net architecture. You can see here I'm normalizing the data, just kind of doing the math. And here is, you know, basically from here, this is what you probably did, right? Train, test, split.
Yeah, but I first reshaped it to 30 by 28,800.
Okay. Well, this is, like I said, this is just an example of flattening it. And so
Yeah.
you can take a
I
look.
thought I did flatten it, but I guess not. I'm not sure.
Yeah. Just, I mean, well, I'm just saying if you, I don't know, right? But the results were not good. So I'm just suggesting something.
Yeah, I'll definitely look at it.
Yeah, definitely look at it. All right, great. All right, great job, Kyle. Are there any questions for Kyle, guys? No questions. Great job. Thank you very much.
Thank you.
All right. Who would like to go next?
I think we will, Professor.
Okay. Well, can you give me the names and everything, and then?
Okay, my name is Iqbal Michael, and my partner is Miss Singh, Nupur Singh.
Okay. Is she here?
Yeah, I'm here, right here.
Good. Just the two of you?
Yes.
Yes.
Okay, excellent. All right, guys, share your screen and you may begin. Or so just sorry, it's 3:16, guys. Do you want us to take a 10-minute break or?
I think we should finish this presentation.
Yeah, we don't have to take a break, right? If you need to step out for a few minutes, just step out and then, but don't need to take a break. All right, great.
Okay, my name is Iqbal Michael, and my partner was Nupur Singh. And our project we work on is a classification of the spam or ham, mean either they are spam or not. So, hold on just a second. Please forgive me. Can you guys see this?
Yes.
Okay. So here's the definition of machine learning, which we
You
have
don't have
learned.
to give us the definition, right? We know
Right,
it.
right.
Get to the, because we don't have that much time.
Okay, so what we learned throughout the supervising learning under machine learning. So we used the pipeline from the beginning, and we're supposed to be using that. What I think, So this is what we use in our project, which was first we collected the data, formatted the data, then we cleaned up the data and applied the old algorithms and yielding all the accuracies. Here is the data we have, and then we put it in and label this data. V1 are ham or spam, and V2 are the messages. And we can see that the ham were 4,827 and the spams were 747.
What is ham exactly?
It's either it's a message or it's a spam.
Can you give me an example? So spam would be like, hey, click here, win a prize, versus, hey, how are you today, is ham. Is that what you're saying?
Yes, and the spam will be something, you know, which doesn't belong to this. It's something spam, like we get in our emails.
So you guys annotated yeah, I can see that. Spam urgent, 1 week free versus ham. Okay, got it.
Okay, so this is unbalanced data set. The total was 5,574.
Okay, so this is your small data set. Okay.
Yes. And in the step 1, we imported all these libraries because that's what is required to run the code. And here we can see on the left side, before and after when we labeled it. So the ham is a 0 and spam was 1. We can see on the right side under the V1, 0010. So that describe what is a what. So we are changing to 0 and 1s. Here is the step 3 in pipeline, using a pipeline. So we cleaned it all, removing the punctuation, converting each word to the lowercase. Our code describe all that. And then when we're done with all cleaning and tokenizing, here was the final message, what we got after cleaning. And these are the, if we enlarge that, these all we put it in alphabetic, these all features. And from here, I think I'm going to give to my partner, Nurpur. Can you hear me?
Yes. So the next step after extracting the features was like first creating a corpus, that is vectorizing the data. That means we basically collected each word and its frequency in each of the email or the messages that we had, and then we produced a matrix out of it. Can you move to the next slide?
Sure.
Then obviously we had to split the data. So we used a test size of 0.20. That was 80 training.
So just very good. Everything is sounding very good so far.
Right.
What are the dimensions of your X and your Y before you continue with this? Roughly speaking.
You mean, Iqbal, would you like to please explain?
Just the matrix X and Y, what are the dimensions?
I'm sorry, Professor, we really didn't check that part because
You can tell me, I mean, you just told me that it's 5,400, right?
Right.
So that's
okay, I see what you mean. I
just want to see your understanding of it. So
yeah, I think it was 8,800 or something.
8,800. What is 8,800?
The dimension of the data?
The features?
Yes, it's when we did a study about this data set, it says that this data set has about 8,348 labels and 1,000.
Not labels. Features. Labels.
Features. Yeah.
Okay. So say that again.
8,348 features.
Okay.
Yeah.
Sample. 5,000 something. How many labels?
2.
Okay, good. And then your values were binary or frequency based, right? The count.
Yes.
Okay, good. All right, so to me, it sounds good. All right, go ahead. Please continue.
Yeah, so we split the data that was in 80% training and 20 for testing, so that we could test for the underfitting and the variance. Then we obviously can go to the next slide, Michael. Yeah, so then that was the final step of applying the classifiers. So we started off with using a decision tree classifier. So if you can go to the next one. So upon doing the decision tree classifier, we saw that after breaking down into smaller subsets, we saw that the confusion matrix showed us that 943 were true negatives and 137 were true positives, that is spam. And we can see the precision recall in the F1 score, which tells us like how precise the classifier was and how many instances basically it classified correctly, so that we did not miss out on any significant instances to balance the precision and recall, both of it. Then we applied the KNN neighbors classifier. Go to the next one. So this also had a pretty good accuracy of 86.8, and you can see the confusion matrix as well for the same. And afterwards, we applied the random forest classifier.
You really should be looking at the F1. So especially when you have a somewhat imbalanced data set.
Yeah, so for 0 and 1, like for spam and not spam. So the precision for both of them and the F1 score. So for having not spam, that is 0, is 93. And for having a spam is 20.
This is a perfect example of how in an imbalanced data set, accuracy is misleading. Look at the value in accuracy is 0.86,
Yeah.
right? So you're going to say, oh yeah, that's excellent. But that's only because there's a dominant class. If you look at F1 score, and if your goal is to predict that, find that class 1, it actually does very poorly at 0.20.
That is true. Exactly. Yeah.
So that's so it's fine. You know, results are results, but I wanted to point that out.
Yeah, of course.
Great. Keep going.
So after that, we did the random forest classifier. For that, we had the F1 score for 0 as 98, and this did pretty well for detecting the spam, which was 89.
It does well.
Yeah.
Okay.
It does really well. So after analyzing all of these, then we also had the logistic regression, the binomial logistic regression model, where we categorize into 2 classes, and we saw that the F1 score for 1 was 88%, which was also reasonably well for this data. And we drew the conclusion and analyzed all the classifiers and said that, if you can go to the next slide, Michael, that even the SVM, sorry, I missed about the S.
Well, but here SVM is misleading because usually it does.
Of course, it underperforms. Yeah,
but it's because I'm guessing it's because your parameters are not right. You know, that gamma and that cost are 2 values that you need to play with when you're dealing with SVM.
Oh, all right, okay.
So that's why you're getting a bad result.
Yeah, that's why we saw that the SVM does not perform that well, because obviously, as you say, that it can be error with this sample size, and also we didn't train it properly. So coming on.
What about Keras? Do you guys have a neural net, deep neural net?
We didn't have the time to do with the neural network for this one, but hopefully when we submitted the thing, like we'll have everything in place.
Okay. All right.
Yeah.
Anything else?
And then plus, Professor, that was a big mess. The GPU we were trying to work. My computer is totally crashed because I don't know what happened with these data sets or using a GPU. So I'm lucky to be online with this.
So this is only the small data set. What about the big data set?
We started working on it, but eventually it stopped running. So we just wanted to present whatever we had today.
So you're just presenting this then?
Yeah, we're just presenting this one. We'll have the big data ready and we'll submit that as well, but we don't have the final results for the big data.
I see.
Yeah.
All right. Are there anything else that you guys want to say?
No, that's pretty much it. Thank you.
These are the
final questions for this group, guys. Right, so I will write down here that you did not have the big data part. All right, great, thank you.
Thank you.
Yep. Who wants to go next?
I think we can do this.
Ben, you guys are going next?
Yeah, yeah.
All right, who's in your group?
Changshi and Zihao.
Okay, so Ben, Sao.
Uh-huh. Oh, wait a minute. I'll just share my screen. Yeah, can anyone see it?
Yes, okay,
Yes.
so let me write down. So there's 3 people in your group.
Yeah.
All right, so I'm writing this down.
Wait a minute. Let me just how to show, never mind. So our project is pretty like ship versus deer. And we get the data from C14 data set from which we select 1,000 pictures of deer and 1,000 pictures of ships for training and makes 500 of deer and 500 of ships for the test.
Okay.
And we basically runs it in a collab environment, and the package we use include OS, NumPy, and Matplotlib. And we can see the images and the features of it. And the first step is to load the data set and configure the path. And we divided data set into 2 categories, train and validation. And for each directory, we have 2 folders for ship and data. The next step, we just check how many images are used for training and validation, and we set the model parameters.
So your images, what is the dimensionality of your images?
What?
What's the size of your images?
You mean the whole data set?
I think it's in the second page.
32 by 32 RGB, or is that the size?
Yeah.
Yeah.
Okay. Yeah, I'm seeing that there. Okay, and then 2 labels. What are the classes? Deer and what's the other thing?
Ship.
Ship is in boat?
Yeah, boat.
You're comparing boats to deer. Okay. And then samples was 1,000, right? 500 and 500 each.
Yeah.
Right? Okay. Got it.
And we processing the data and formatting the picture into floating tensor. And then we load the image and resize it into the same size. Then it's the visualizing the training image and define the model. Well, in this model we have like
So you use the convolutional neural network?
Yeah. We have 4 convolution layers, and each with a max polyline.
Got it.
And next is compile the model and train it. That's the result, and I think Chenxi can talk about the results.
Yeah, I think because we try a lot of convolutional model and we change parameters, and finally we get the 100% accuracy, training accuracy, and the validation accuracy also.
All right.
And this is that's
only your small data set, right? Where's your
Yeah.
big?
It's actually we didn't have GPU, so we just use the Colab, so it takes
But this is only 5,000 samples, right?
Yeah.
Yeah.
1,000. So this would
1,000.
be, you labeled it. So this is only your small data set. Where is your big data set?
It's a 2,000 trained data set and 1,000 and test data set. Yeah.
That's right. But what I'm saying is if you only have 1,000 images that you labeled as deer, that's only part A of your project. Whereas part B, you've seen the other presentations, right?
Yeah, I think so. We need.
What?
You don't have that?
Yeah, we don't have maybe a lot data set.
All right. Anything else you want to say?
Oh, that's it.
That's it. All right, guys. Any questions for them? No? All right, great. Thank you. Next group.
We would like to go, me and Rishita.
All right. Go ahead, please.
Rishita, can you share the screen?
Yes, 1 minute.
Okay, so.
Can you just put up your name so I can write them down, please?
Okay, sure. 1 minute.
All right, thank you. Make that a little bit bigger, will you?
Can you see, Professor?
Yes, I can. I'm writing it down right now.
Oh, sorry.
Hold
Okay.
on. Go back. Go back.
You want me to start?
Go ahead, please.
Okay, so we have selected 2 projects. The first one is like analyzing Titanic disaster using machine learning. The basic aim of the project is to predict the survival of a passenger on a Titanic based on the data set. We got this data set from a Kaggle website. The data set information has been divided into two data sets, that is test set and the train set. For the train set, we provided the outcome whether a passenger survived or not. We use this train set to generate predictions for the test set. For each passenger in the test set, we have to predict whether or not they survived. So we went through a process in which we first cleaned the data, and then we did the integration and then the data transformation. For the missing values, for age and fare features, we fill them by like median values of those features. Next slide. Yeah, Rishta, can you explain the outputs?
Before you get to this, though, can you talk about the data set, your X and Y? How many samples, how many labels, how many features? What are the features?
The CSV file contains the following features or fields. It has passenger ID, passenger class, name, sex, age, number of passengers, siblings or spouse on the board, number of passengers, parents and children on the board. It has tickets, fare, cabin, and city where the passengers like boarded.
So how many? I just need the dimensions.
Oh, for the training thing, we had like 1,000+ features, and it has like 1,000 change columns. And for the test, it has like 800 change columns. I don't know the exact number of columns. And
right? So I'm confused. So remember, samples is the number of rows, columns is the number of features. How many do you have?
I think we have 1 label and 11 features.
Yeah.
1 label and 11 features. You would have 2 classes, right?
Mm-hmm.
11 features. How many samples do you have?
I guess like 1,000 change samples.
1,000.
Mm-hmm.
How many are survive? How many are not survive?
Rishta, can you put on the graph?
Yeah, sure. This one, right?
Can you make that a little bit bigger, please?
Yes, sure.
So what is it?
Yeah, this is here. 0 is the survived and 1 is, 0 is not survived and 1 is the survived count.
So there's only 20 that survive or not survive, and then there's 42 that survive. Is that your whole data set?
No, Our whole data set contains 1,000, but this is a test futures.
These are the test results. Okay.
Yes.
All right. So, but roughly, how many in that 1,000 are of survive versus not survive?
Total
roughly like-
1,000.
Yeah. In 1,000, I think 600 change have survived and like 400 change have not survived. Based on the test results, we could predict that.
600 to 400. And then
Yeah.
how many features? 11 features, you said?
Yes, 11 features.
Okay,
12 features and 1 label. Sorry.
1 column label of 2 classes. Okay.
Yes.
All right, go ahead.
Yes.
And since the data have missing or incomplete fields, an important step in a building any predicting system. So we filled had missing values that had to be filled in. The field name, while being useless itself, contained passenger's title like Miss or Mrs. We also used passenger's surname to distinguish families on the
I will
board
show
of
the code.
Titanic.
1 minute, Dakshita.
Yeah.
Yeah, this is the code. Yeah, you can continue.
While the features, for example, passenger ID, survived, P-class, age, parts, and fares are numeric qualities, and then name, sex, and all are then sustainable qualities. For a point-by-point highlight building, we initially examine the features like age, and then age, and then name, and we use several predicting algorithms like in Keras, and we got we achieved a score of an SKLearn, and we achieved a score of 80.383% of correct
Show the
predictions.
results. Can you show the results?
Yeah, sure.
Okay. So in the 70 range, okay. And there's Keras. What are the results of Keras? Talk about your neural net.
Keras is 0.80% accuracy.
80%.
We almost got similar. Yeah, we got similar scores.
We got similar scores. This is
what is the architecture that you use for Keras?
Keras architecture. It's normal logistic regression architecture only we used.
Only logistic regression.
Yeah.
No, that's fine. I'm not, I'm not saying.
Yes.
That's fine.
Yes, logistic regression with categorical data.
All right.
We also did another project like which is a small data where we used SKLearn and Weka features.
So this one would be your big data, but this is only 1,000 samples.
Yeah, we thought actually we didn't found the data much more for Titanic. We will found it and we will combine it to dataset and we will
Until,
try it again.
Until we submit, we're gonna add more features and more columns to it.
So you're saying, well, big data just means more samples, really. So you're saying this is your big data then?
Yes, this is our big data. As of now, we found only 1,000 samples, 1,000 plus. So
I understand. And then now what you're going to present is your small data where you've done the annotation yourself.
Yeah, we used the tweets, and then we did the SKLearn for that. We did the sentiment analysis and got
analysis. Okay, go ahead.
Yes, this is the movie review. Yeah,
which is a raw data we took from a Twitter and then used an SKLearn. SKLearn features like decision tree, logistic regression, and all to get a prediction. Like for the sentiment analysis, is like positive or negative, where we get a positive reviews, and then where we divide it into positive or negative reviews.
Based on the message type, whether it is positive or negative, we divided it, and this is our results for SKLearn. We got the naiveBayes, we got highest accuracy. Remaining all we got less accuracy. Do you want to see our code, Professor?
I would like to know how you came about the data, X and Y?
X and Y.
How many samples, how many labels, how many features? Same question as before.
Actually, we got only two. One is the label is that whether it is positive or negative based upon that 0 and 1.
Okay.
And the features of the sentences, based on the sentence, we found we used the sentiment analysis and we found whether the sentence is positive or negative.
I understand that, but how many samples, how many features did you have in your data set?
It's a raw data, Professor. It's a tweet. Yeah, it's a tweet. Those are the tweets we extracted. Yeah, it's a text data.
How many tweets?
Like
around
400?
1,000, I think.
Oh,
no, I think so. Yeah, around 1,000.
How many features? How did you extract the features? Show me how you extracted the features.
Yes, one.
How did you go from a tweet to the actual features?
Actually, we copied that into JSON file, the data.
Okay.
Then we extracted, we cleaned the data, and we vectorized the data with the by appending our sentiment to it. Then we divided it into X and Y.
Okay, I can see you use count vectorizer there, so that's
yes, we used vectorize.
What we covered in class.
Yeah, this code is almost the code which you got from the GitHub that you gave with little more features, adding add-ons and all.
Yeah. Okay. So this is your small.
Yeah, this is our small data set.
And the other one would have been your big data, which wasn't very big.
But we will try to add data, Professor.
What were the results of this one? Can you just show? Did you do net on this one as well?
Yeah. No, I didn't do this in Keras.
Okay, so only SKLearn and your best
results. Only SKLearn.
What was your best algorithm there?
naiveBayes.
naiveBayes. Okay. All right. Anything else that you guys want to talk about?
No, this is it, Professor. Thank you.
All right, great. Are there any questions for this group, guys? Any questions for them? No questions? Yeah, so I think it's good, except for the fact that you didn't do the big data. I mean, your analysis seemed correct to me. Titanic there.
Yeah, but then we're gonna add a few more data.
What were the results of that Titanic? Can you just go back to it? I just want to see this table for Titanic.
Yeah, sure.
You said
this is the results of
this one. You did use Keras. What was the result here?
This is for Keras.
Yes, this is for Keras.
What was the F measure? Can you go back to that?
Oh, we didn't dig that.
No, it's 0.878.
Okay. All right, that's fine. All right, great job. Thank you.
Thank you.
Thank you.
All right, guys. Who wants to go next?
Professor, I have a question.
Yes, go ahead, sir.
Since if we didn't add a big data, we did work on it. We presented before this group. So when we submit our assignment, can we add in that one?
You can add it. I mean, sure.
Okay, I just want to make sure that we're not getting any deduction, a big deduction in that.
You are going to lose points for not presenting big data today, yes. But you can put it in the final report and I'll review it, and depending on what you do, if it looks really good, that you've done a lot of great work, that could upgrade, what do you call it? Improve your grade.
Appreciate it. Thank you so much.
Okay. Next group.
I think Mitch and I are ready to present.
You guys ready now?
Yep.
Yes. No feedback in my mic this time, I think.
The mic doesn't sound great, I'll be honest.
Dang. All right.
There's something going on with that microphone. Right, guys?
I actually switched, but it is what it is, I guess.
We can hear you, I think. It's just
Okay.
not muffled somehow.
Yeah, I can at least understand you. It's not the greatest quality though.
All right. Sorry about that.
So are you guys going to present then?
Yes, I'm bringing
Okay.
up my
Marian
PowerPoint.
and Mitch. Okay, good.
Yes. All right. So Mitch and I, for the final project, our objective was to use the techniques that we learned in class to categorize music into correct genres. We did this using 2 different data sets. We had lyrics, which was just text, and then we had audio files, and these were all WAV files.
Okay.
I'll let Mitch start talking about the lyrical data set.
So with the lyrics, what we ended up doing was using the bag of word technique, just as the simplest thing. So basically that ended up being right around 220,000 samples, and there ended up being right around 63,000 features per sample. I think that ends up being like total of 14 billion features. A little bit too big for what RAM could do, so we had to scale that down.
Parameters, right? Not features.
Yeah, yeah.
Parameters in the model, like the weights and everything, right?
Right.
Okay, got it.
So there was 11 classes, which ended up being the genres.
What are the genres? Like country, rock, that kind of thing?
Yeah, it's like country, rock, pop, just whatever the data set contained. So then the data was split. There are 70% for training, 30% for testing. We used a deep neural net that gave the best results for this, so that's the only one we included.
And you're using subclassing there. I can see that.
Yeah, I just figured try and change it up just a bit to
Nice.
experiment. So it was 2 hidden layers, and then 3 hidden layers, and then the output. We used the Atom optimizer with a 0.01 learning rate.
So you went from how many features was it? Like 6,000 to 500 in the first layer.
Yeah.
Okay.
And then the dropout in between the layers just to force it.
Okay.
Those results ended up being not the best. About 45% for accuracy and 20%.
What was the split that you had on there? Was it balanced for the 11 classes?
No, actually, the next slide will talk about that. So basically, the data set was real heavily skewed towards the rock class. Yeah. I think 1, 2.
That's your problem right there. Is probably just break it into categories. 3 or so, right? Rock and metal are probably 1, and then pop, hip hop probably 1. Everything else 1. That would probably improve your results. But yeah, good.
Right. So that's why we concluded the results weren't really that good, because I mean the next 5 I think
it's a highly balanced data.
Right.
Set.
Right. So that was that one. So those are the things we could improve with that.
Ooh,
and then next up, I'll let Marian talk about the audio file.
So just to conclude then, that was your big data one. Yeah, 200,000, right? That was your big data.
Yes. Yes.
Okay. 200,000 count vectorizer. What did you take as input exactly? The lyrics of a song.
Yes.
So a text file of the whole lyrics of the song was a sample.
Yep.
Okay. Then you did count vectorizers. Yeah, so that's going to give you a lot of words, which makes sense. So you had 200,000 by, let's say, 6,000 words. I can't remember.
I think it was 60,000.
60,000 words. That's really large. So 200,000 by 60,000, 11 labels. and you vectorize it basically, so it's frequency counts.
Yep.
And then you ran that through the GPU Scholar or your own GPU.
Yeah, I ran that through my own.
Okay, and then you built a deep neural net of how many layers was it?
3.
3 or so. And then the results were not great.
Right.
Okay, yeah, I got it.
All right. So for the audio files for the smaller data set, we had 1,000 wave files that we used. They each were about 30 seconds long. We converted those into RGB spectrographs or PNG files. So basically, the originals were 720, 720 by 4. Once we reshaped them, it was 200, 200 with 3. So that added up to about 120,000 features. As you can see on the right, that's one of the examples of what the spectrograph would look like. So the x-axis would be the time intervals of a song, y would be the frequency, and then it might be a little hard to see, but you can see the decibel scale on the right.
Right. So I've worked a little bit with speech. So you have the song in the x-axis, then the frequency. Music is broken up into frequencies, right? The harmonics and everything. And then you just, in that third dimension, the color represents the intensity of it, correct?
Correct.
Yeah. So you have a 3, basically this picture, it's, it's like a three things in there with the value. And that becomes an image, right? So basically, if you think about it, you treat speech as a picture. So you converted basically here, every one of your 1,000 wave files into color images, correct?
Correct.
Correct.
Okay, excellent. What is the dimension? And the dimension of this is what, 720 by 7? What is it?
It's
the
200
original
by
720.
Yeah, the new one's 200 by 200 by 3.
By 3. Okay. What did you use for, if you don't mind my asking, to get the spectrograms?
We used a library called Librosa.
Librosa, yeah.
Yep.
Good. All right. And then, pretty much that's all you need to know. This uses like the spectrogram is generated by something called a Fourier transform. But yeah, that Librosa library does a pretty good job. So excellent. You've shown everyone that you can take a wave file and convert it into an image. All right. So now, what are the labels here?
Let's see. So that picture just shows how we just kind of loaded it in. We just read it in with imread, the matplotlib function, and then flattened it. The next slide, I believe, shows the more of the
same idea. 10 classes. Okay, got it.
10 classes. All of them
A
were
little bit
balanced. So there's 100 each.
Oh, so this is balanced? This is balanced?
Yes.
Oh, better then. Okay, go ahead. And you use CNN. Okay. Got it.
Yep. CNN, 4 convolutions with max pool in between, and then just some dense layers, and then the output.
How does it do?
That would be the next slide.
Yeah, it wasn't incredibly accurate, but
it wasn't the best, but I think some of that was part of the audio samples themselves. I think some of them were fairly similar to each other. So the CNN pretty much only performed about 56% on all metrics. What we ended up doing also is rather than take the images, we wanted to compare the images to kind of like the raw numeric data of what the frequencies and everything would be. So that would be like a deviation between the two, a chroma shift, a central spectroid. So just like numeric actual data, like more technical, I guess, physics-based type things.
So you're saying you convert the features to another thing?
Yeah, so rather than take
using the image.
No, so this was doing the audio. So rather than convert the audio to the images, we converted it to other criteria. Basically.
Okay, so how many features do you have? So in CNN, it'll be 28 by 28. In numeric data, if I understand correctly, you have a new set of features, right?
Right.
Physics-based. How many do you have, roughly?
Off the top of my head, I don't remember. I believe it was right around 18 to 20.
Okay. And this does better?
Yes, so both were ran same optimizer, same epics.
Do you by any chance know what these features are?
Yeah, so
Because I feel I know what it's gonna be, but you tell me.
So the features, just going off of some things that Leaprosa had followed. I think it was chroma _ STFT. Let's see, another one was RMSE, which was the root mean squared error.
Okay.
Central spectroid, spectral bandwidth, roll off, zero crossing rate.
Okay.
MFCC.
MFCC is mel frequency cepstral coefficient.
And there's
Yeah,
20
those
of those.
those are widely used in speech. So I understand what you did. Pretty good. All right, and you're saying that it actually did better than mel frequency cepstral coefficients are a mapping of frequency waves to the Mel scale, which is the hearing that we have in our ears.
Right.
So it kind of makes a little bit of sense because we're talking about, songs, right? Speech. So good.
The one more thing to add, the images were also based off of a Mel scale too. So
okay, good. Excellent. But this does better. So did you do a feature ranking of those numeric data to see which ones did the best?
Unfortunately, we did not.
That's something that in a study, you would probably want to report because it would be interesting to hear. I'm just saying, when you're comparing CNN and numeric data and you say that F1 measure is almost 10% or 12% higher, well, then why, right? So getting into that numeric data, ranking the features, that would be pretty good. All right, good. Did you do a confusion matrix here? Just because you had 11 features, it'd be interesting to see where it did better or worse.
Let's see. Yeah, I do have a confusion matrix for the numeric one. The CNN was throwing out some.
All right, let's take a look at it.
Bugs. Marian, if you can stop sharing, I can pull it up.
Yep, we can switch over.
So you did speech and songs were the other one, correct?
Correct.
Great, I like it.
You should be seeing the screen.
Oh, okay.
So this is basically confusion matrix. I just used the cross tab instead.
So the diagonal looks like it's more populated there.
Yep. And then like I said, the one with TensorFlow didn't really, wasn't working well. So I just kind of stopped it.
So what model did the best?
Of the two?
Oh, for this, of the two CNN and numeric data, which model did the best?
The one we did with the numeric one did
And
the best.
and what was it a logistic regression, deep neural network?
Yeah, so it was just a simple deep neural network.
Deep neural network. So did you flatten the images? Is that what you did?
The images for the CNN went in as.
Oh, you did a CNN, right? Okay.
Yes.
All right, sounds good. Yeah, great job. Anything else you guys want to say?
No, I think that's all we had. Marian, do you have anything?
No, I think I covered it.
All right, great, excellent. Are there any questions for this group, guys? No questions. All right, great job. Thank you very much. Who wants to go next? We're doing really well on time. I think there's only a few students left, I believe. Or did everyone go already? All right, so from what I'm seeing here, looks like everyone.
Actually, my group hasn't gone. We were
Oh,
just
okay.
still running the epochs.
Yeah, you would be the only group left. Who's in your group?
Just me, Sydney, and Gianna.
Okay, all right. So you're the last group, I think. Is there anyone else, guys? What I'm seeing, there's only one group left. Make sure you let me know. You have to present today. So so Sydney and Gianna.
Okay, so let me load up our PowerPoint.
Okay.
Okay, so we were mistaken. So we did for our large data set, we did parking violations in New York City from 2013 to 2014 for our large data set, and it was a little bit over 1 million records. I think it was 1,050,000 records.
Something like that.
Our small data set was also parking violations, I think, in Maryland.
Yeah, it was in Maryland 2019. They're both in 2000. Well, actually, the one that we found for New York City, the one that we currently have was like in 2011. And the Maryland one was in 2019. And it was a bit smaller. It was a few 100,000.
Yeah, it's about 350,000. But we didn't realize that we had to build the data set ourselves. So when we submit, we will probably have a different data set for our smaller data set.
Okay.
So as she said, it's from Maryland in
Can you
2019.
your screen is showing
Oh. Why is it?
There's, if you go to the top, it says display settings.
There we go.
Then this, yeah, thank you.
Okay. So as you can see, it's got a couple of the core features that we wanted, like the vehicle color, the year that the vehicle was plated, and the type of plate that it is. So like a commercial or what's the other one? I'm drawing a blank, but and then the vehicle type as well. So like the make. This data, this is just some of more in detailed view on what the actual data sets are. And we need to trim some of these down because they don't
So are you presenting the big data part right now?
No, this is the small data.
Okay, so just tell me that.
Yeah.
All right, so small data, what are the dimensions then?
Gianna.
Of X and Y.
The X and Y. So there was about 13 X's and then 127,000 Ys. No.
No.
Other way around.
No, you need to tell me how many samples, rows, how many features, columns in X, how many labels in the Y vector.
So we had 13 separate features that we used, as you can see on the left. Okay. And then all the columns we had in data. Were you
the
saying
vehicle, we were using the vehicle color as the Y.
Vehicle color as the Y?
Yes.
So what is your model trying to predict?
It's trying to predict if there's any which type of color car gets the most tickets.
Okay.
Well, in this case, ticket number is actually our main Y. Like that's the different thing that they're looking at, and then it's trying to predict how likely the color of a car will get chosen. And as you see a little bit later,
if you drive a red car, you're driving fast cars.
Yeah.
So
something like that.
this is parking violation. So this has to do with them parking and
Oh, it's
maybe not
parking.
paying the.
Parking.
So if
So-
they park in a certain area, are they gonna get
So
a
if you
ticket
drive-
basically?
So if you drive a red car, you're inconsiderate person who buys expensive cars also and is inconsiderate about parking.
Yeah, as you can see, Toyota is actually the highest number of the brand of cars that actually got parking violations. As you
That
can
should have been
see,
a better one, right? As a label predicting the model. But
That's
you guys
true.
predict the color. No, I'm just
Yeah.
saying. I mean, it's fine what you did. So I'm just trying to. Whenever you do something like this, what's the argument, right? So you're saying a person is there a bias basically that the person that gives the ticket is more likely to give somebody a ticket if they have a red car versus other colors?
yeah.
Yeah. And I think the biggest reason Toyota was so high was just the amount of service vehicles and like business vehicles that are Toyota.
Okay.
Like Tesla doesn't have any like business grade vehicles, so
Yeah, that makes sense too. Okay. All right. So again, how many samples? 127,000?
Uh-huh.
And this is your small, correct?
Yes.
13 features, which we've talked about.
Mhm.
And the label is which one? The color?
Yeah.
And click on that. Oh, this is a slide, right?
We were taking a picture. There's a picture of the vehicle color.
How many classes do you have? If color is your labels, how many labels?
Then there should be just 12 other than color, right?
So you
But
have no. Again, you have 13 features or 12 features. You have 127,000 samples. How many labels? How many classes? That would be by the color, right? So
there was a lot. I have to give me a second because I think there was over about 30. Let me see.
31.
30 different types of colors, including
I thought there was 26.
Was there?
Based on the confusion
So
matrix.
you had 26 labels then?
Yeah.
For different types of color. They had a bunch of them, and some of them were mislabeled. So
Yeah, we need to compress some of them, like blue and cyan have two
6
different.
labels, and I'm looking at your results right now.
Mm.
Is the thing to the right the confusion matrix?
Yes.
Mm.
It's almost all zeros. Do you see that? And then the diagonal, there's nothing there.
Yeah, that's what I was gonna get into once we started explaining the data, especially once we get to SKLearn. You really see with the F1 measure that I think the amount of like colors that we have really led to.
Yeah, it's too much. It really, what you could have done is red versus all, for instance, or
red versus all.
Yeah.
That's a good idea, actually.
Because but the problem with that hypothesis is that you're basing it on your assumption, that people that have red cars get ticketed more, but that may not be true. You know what I mean?
Yeah, actually, I think it was white cars that actually got ticketed the most. I guess because they were just the most common type of car you see on the road. It was like that in black.
Yeah. So I don't know, but what I'm saying is definitely 26 labels is too much.
Okay, because we had a lot of the things because I ended up converting all this data from actual words to numbers, and with the big data set, it actually took me over 18 hours to do. So, and I think it's just too many labels because I had over 1,000 labels on the large data set, while with this smaller data set, it had a more reasonable number.
I understand. Okay, good. Keep going then, guys.
All right, so I forgot to mention first of all, this was so we ran a 70-30 split, and then we also ran a 10. We ran the cross validation folds as well. None of these it did not do very well on any of them.
But maybe we can cut down on the colors and the numbers would go up. I think the problem was with the cars, they would have 2 colors, and I'm not sure if I should just combine them. Like they had tan and white, white and blue, and I would make those separate classes for them.
Many. So in classification, you don't want these many classes. It's not gonna work.
Okay. So maybe we should switch to vehicle make then.
Make
Yeah,
has a lot of them too, though. That's the
Well, yeah, but
problem.
like we could.
I would recommend only 10 classes at most.
10
At
classes,
most.
okay.
Yeah, at most, usually.
Okay.
So it's gonna create a, give me a sec, guys. My battery's dying.
So we can just do color or the make, like you said. And I guess, because we put in a lot of extra data, so.
What do you mean?
Yeah, like there's a lot of extra stuff that doesn't need to be in there, like what street the violation occurred on.
Code violation,
Well,
like
the
what type of,
features can stay in there. Your problem is really only the labels. You can always have. It's fine to have thousands and thousands of features. You know, that's okay. You saw that previous group. They had 60,000 features because they took every pixel from an image. That's fine. But remember that a model needs to differentiate between classes, and the more classes you give it, the harder the problem is going to be.
so give it
Plus,
less
I'm betting
classes.
this was a very highly imbalanced data set. You're saying that some colors were like blue and gray.
Yeah.
And
Yeah, it wasn't
imagine
balanced.
that there's going to be very few of that versus white. So white is
Yeah.
going to be highly dominant. Blue and gray, you're going to have a few examples of that.
Actually, there was a lot of grays, but the problem was the mixing of colors. They had some that was like gray and white, and then so I made
Yeah,
a
but
separate class for
he's
that.
saying his point is though that there's still like white is still one of the predominant ones.
Yeah.
Yeah, if you have 100,000 white cars, but then you just have 100 that are gray and purple, whatever that is, that's it's too imbalanced for machine learning to figure things out.
Okay, so yeah, and within our 70-30 split, random tree actually did the best. I don't know why the screenshot got cut off. Oh, it had about a 30% accuracy, but it still wasn't very good.
A good observation. Decision trees do well on these types of problems. They zero in on specific features. I mean, it's not gonna be great, but they do.
Yeah.
You are right.
I tried running a random forest, and I was on. I let it run overnight.
Did you run Keras on this?
Not on this one.
No, but on the other one.
Yes, or we're in the process of it right now. Okay, so then it was a very similar story with our cross-validation tenfolds.
Still in the small, correct?
Yes, sir.
Okay, go ahead.
So it's still not very well off, as you can see.
But there's a lot less zeros on the right side than it was on the other ones.
Yeah, but you can still tell, like, by the time it gets to AE, it has no idea.
Yeah, it's too many labels for sure. Okay.
We'll cut that down. But how come look at this one? AE actually has a higher number than the other areas, like more the middle area actually.
Yeah, but it's incorrect.
Yeah.
Jana, what you want in the confusion matrix is the diagonal. The diagonal should have a lot of values, and everything else should be very low.
Yeah, like A1, and then but you see B2, there's nothing for B2, so it didn't properly classify any of B.
Right. And when you see these things, it's telling you that there's a class imbalance where it's favoring the classes that have a lot of samples versus the ones that don't have.
Yeah, that color, like the color for B might have been something else, or whatever we put it as.
Again.
So we had 100% error on that one.
Yeah, well, this was just the rules base though. I've never had good luck with 0R.
Okay.
Where is? And then a random tree again as well. As you can see, it did a little bit better than the others, but still not.
Okay.
There is a lot more diagonal on that one, but it's not where it needs to be. And then we also pushed it through SKLearn. We're still working on the SKLearn section. We managed to get some metrics, but some of the other metrics were so low that it told us that it.
Yeah. No, that's fine. Okay.
But our decision trees, like you can see, the F1 measure isn't even.
Yeah. So that it's gonna be consistent with the previous one. Okay.
Yeah. Logistic regression did even worse.
0.14, a number you didn't think could get
Random,
that low.
Yeah, random tree again did the best out of all of them.
Which makes sense, as I said, with trees do, for whatever reason, do a little bit better when you have this kind of data. All right, so now you're moving to the big data, right?
Yes, so actually I need to stop sharing the slideshow and then share my actual screen because we haven't gotten to putting this on the slides yet. So let me load up.
And that's 1 million records?
Yes, there's over a
Yeah,
million.
it's over 1 million.
So again, X and Y, what, number of features, number of samples, number of labels.
It was wasn't the Y the registration number? Let
I don't
me
know,
see.
you tell me.
Oh,
let
that?
me
I
pull
thought
up
it was
my-
that.
What did you use as labels for big data?
Yeah,
Oh
I
no,
need
summons number. No wait.
Let me get my screen share up now that this is actually on there. Okay.
Oh yeah, it was you did vehicle color for the Y for the large data set.
You also did color for this one, so you'll
Yes.
have the same problem.
Yeah, we hadn't realized that going in. But like I said, we plan to do a lot of changes in the next couple of days to get it all up to where it needs to be.
Your input actually was very valuable in helping us get this to work properly because yeah.
Yeah. Okay. So you should be seeing my Excel sheet right now, right?
Yes.
Okay, so this this is actually, and it's actually a CSV. We're just loading it
In Excel.
Okay.
Yeah. So we have a lot of the very similar data, like the registration state, the type of plate that it is, which is again is like commercial or residential, and
So features is roughly 12, 20 features, right?
yeah.
Okay, and then the labels is vehicle color, so 29 colors again?
No, there is like, as you can see,
Oh.
I hit over 1K in different labels.
think about it,
So for
1
color,
class labels.
color might have had a few hundred of classes.
But again, you guys understand the point, right? That
Yeah, we understand a lot more now than we did.
way too many labels.
Yeah, that's why it took me
Learning
so many
algorithms
hours.
do well with like 3, 4, right?
Yeah, so we'll revise this before we have everything turned in.
All right,
So
samples. So in summary, samples about 1 million, features about 20, and then labels.
Too many.
1,000.
Labels are over 1,000.
Okay, so talk about your models then, please.
Okay, so it's on my desktop. It's still running the epochs I set up. However, I figured it wouldn't get done in time, so I set up Google Colab. I don't know if you've heard of it. It lets students use AI resources for free. We only ran 5 epochs, and it's still not.
It's a steady decline.
So the accuracy is not improving yet.
No.
No.
Okay.
And you can see that.
It's not going to do very well still, but
Yeah, we need. Knowing what we know now versus what we knew 10 minutes ago, there's a lot that we need to fix.
So let's look at your model then. What neural network are you using? The architecture.
This was
Keras,
the Keras?
TensorFlow.
Yeah.
Yeah? Keras?
Yeah.
What's the architecture? How many layers? How many neurons?
Oh, you have to scroll up into the code area. You specified that in the code.
Yeah, well, we hadn't actually gotten around to changing up what it was actually running. So it's actually running what Keras was running. So I think it was a 2x1.
So what we did in class, you're saying?
Yeah, we haven't modified it yet because we were still working out what we were.
But you are
doing.
reading your data, correct?
Yeah, at the top you can see here it's loading in our CSV and
CSV X, Y. Okay, so there's your X and Y. So when I ask you the questions, this is what you should look at. So 0, 12. What I would recommend also is put a couple of, in the future, just for your own reference, put a couple of length. So that'll give you the number of samples, the number of features, you'll have all of that.
Okay.
And then scroll down then. Let's look at the architecture a little bit so I can see everything you did. And then you have, so it seems like just a logistic regression.
That was the first.
Notice also your cross entropy there. It says binary cross entropy, but you have many labels. So you probably have to change that.
Oh, so we can do a different type of entropy. Oh.
Yes, a multi-class, right? Because you have more than 2.
Yeah.
Okay. All right.
And it hasn't gotten to running.
The deep neural net.
Yeah, it's still.
You don't have, so look at, you don't have that many neurons in your network either. 4, 4, 4, 1. It's basically the one we did in class.
Yeah, like I said, we haven't had a chance to
You have
specialize
to
it yet.
play with those architectures.
Yeah, with this accuracy, we couldn't really figure out what to do, but
What I would
yeah.
suggest is if you want to stick with that color, is just like try like white versus all, or white versus reddish colors versus the rest, you know, something like that. But try to balance the data set.
Okay.
Yeah. All right. Not bad. Anything else?
Like I said, as far as the small data set goes, we're probably going to replace that with an image training set. We didn't realize that we had to make the data ourselves or scrape the data.
Yep. All right. Great. Anything else, guys?
No.
Oh, all right. Any questions from the audience? No questions. Great. So I think that was the last group, right? Anyone else? So great job. I think, you know, very interesting projects. I really like the fact that we had variety and we can look at different things. So hopefully this, you know, looking at these presentations was useful. There might be some questions about these on the exam a week from today. Otherwise, don't forget to submit your Keras homework and this, of course. I think I've opened a Dropbox for this, so you can submit there. All right, so that's it for today. You know, I don't really have anything else. We are done for the class.
One quick question.
Yeah, go ahead.
I didn't hear, do we both have to turn in the report or just one of us?
Please do that. It just makes it easier for me to grade.
Okay.
So everyone submit their report files, even if it's the same per group.
Okay.
All right. Thank you. All right, guys. So we are done for today. I hope you liked the class. I anticipate that, you know, in time, this will become even more used, you know. So certainly. Great. All right. So that's it for today. I'll stay for a few minutes if you guys want to ask any questions. I'm going to stop the recording.